So, alright, welcome back to particle physics and the Standard Model. This is lecture 36, okay. And as you can see here, in the last lecture we saw a couple of important consequences of spontaneous symmetry breaking in the electroweak sector. The first was Goldstone's theorem, which tells you that for spontaneously broken continuous symmetries, you will inevitably have massless modes that are called Goldstone bosons, and we could explicitly very easily derive that 3 of the modes sitting in the Higgs after electroweak symmetry breaking actually had 0 mass, right. And for every generator that you break, for every generator of the symmetry that you break, you will have one Goldstone boson. Okay. This is not something we will prove in this course, but I encourage you to go look at Schwartz for instance or other references on the internet to see how the proof comes about. It is a non-trivial proof. Okay. And we saw already that there was one example that we had already seen in the course, but we just realized what it is exactly, namely pions. So, pions are Goldstone bosons, but the reason they are not massless is because the quarks themselves are not massless. So, we began with an approximate symmetry and ended up with approximately 0 mass. Okay. The next observation we were trying to work out is the actual masses of the gauge bosons themselves, and for that we took the kinetic term using the that includes the covariant derivative, the kinetic term of the Higgs, and from there we were trying to single out the masses of the gauge bosons, right, the W's, the W bosons basically, W1, W2, W3. In that process we saw that it was convenient to define the combination W1 plus W2 as W plus and W1 minus IW2 as W minus, right. So, when we did that, we could write down one combined mass term for both the W plus and W minus. So, if you feel uncomfortable with this, you can just write this as W1 squared plus W2 squared, okay, no problem, because this is how we wrote it in the Procol-Lagrangian, right, A mu squared. So, you are absolutely welcome to write it this way, but this is a shorthand notation to see that for charged states you just marry up the plus and minus states and you get a single mass out. Okay. Then we saw this another strange combination of W3 and B mu getting a mass. It was not just B mu getting a mass or W mu getting a mass, it was this combination itself that seems to get that mass. Again, you are welcome to think of just W mu getting a mass, B mu getting a mass, there is a cross term with W mu, B mu, right, but that does not give rise to a clean interpretation of what this field is. So, might as well write this as a combination. Okay. Now, we will see what this combination means. Okay. If it had not been obvious last time, I am going to give this combination a name, that is the Z. Okay. So, that I can now write the Z boson squared, the mass of the Z boson squared is what from here? It is G1 squared plus G2 squared. There is a 1/4 outside, right. So, how does the mass go? The mass term? There is a half field squared, right, half mass squared field squared, right. So, that means the mass is this. Okay. So, this tells you that the Z boson, there is something special here. Not only is the mass proportional to V, which is what you expect, that is ultimately what we wanted, right, turning a field into the constant, but the mass of the Z boson explicitly depends on both the U1 universal gauge coupling and the SU2 universal gauge coupling, G1 and G2. Okay. It is not just an SU2 weak gauge boson. here this is literally, this is very much an electroweak gauge boson, both hypercharge and the SU2 weak take part here. Okay. So in the same breath we can also just write down the W mass. What is that from here? So that is just G2 squared over 2 V squared. So the W still remains very much a pure weak boson. Why? It contains only G2. So when I say pure weak, I mean the SU2 weak gauge symmetry. Okay. All right. Then we mentioned this tan theta W, right? Why did we have to write it this way? We did not have to actually. We could have just written everything in terms of G1 and G2. But if you put it in this form, right, it gives us the notion of a mixing angle, right? In the Hamiltonian, if you want, there is a mixing between W3 and B mu. So if you want to rotate to a mass eigenstate, you get a mixing angle, correct? So that mixing angle is given by theta W, and this is a measurable. Clearly you can measure things in both interaction eigenstates and mass eigenstates and tell how much mixing has happened, and the measurement is the measured value. I am not going to write the error bars here, but the often quoted value is 0.23, okay, up to a few decimal places. I think there are I think they have measured it up to 3 or 4 decimal places. Okay, you can go check. And what is this theta W called? It is called the Weinberg angle, or just the weak mixing angle, okay, however you want to call it. Okay. Now something else has happened here, okay. I wrote down the mass for this combination, yes, but what about this combination? We just saw that that combination did not pick up a mass, right? Why? Because I hit it with a 0 here and a 0 here, right? So that means I can now identify that as the orthogonal combination. It should be clear from here, but in terms of the cos theta and sin theta, it is even more clear, right? So let me write down that combination orthogonal to the Z combination. Okay, you see, right? This is orthogonal to this. Agreed? So what is this combination? What name shall we give this? This is exactly the photon. Okay? Would you agree? Right? Because what is the mass of the photon that we have picked up at this point? 0. Correct? So now you see how electromagnetism arises from the breaking of the electroweak symmetry, right? This is exactly what we mean by, when I had been writing it down before, this is what I mean. So the SU2 cross U1 breaks down to one combination, one symmetry where the gauge boson is still massless, and that is the gauge boson we call the photon. And now we can assign not hypercharge, but a different thing that is charge under this new U1, that is exactly what we call charge, electric charge. Okay? So, there you go, that is electroweak symmetry breaking for you. Okay. Now, there is one more thing that is super important. Okay. We have to put the two observations side by side. Okay. We made two observations about the Goldstones and the gauge bosons. This is where the physical understanding comes. Okay. We created three massless Goldstone modes, right? And then what used to be three massless gauge bosons, right, acquired a mass. Okay. Of course, the three massless Goldstones correspond to three broken generators. Okay. So, what's really happened here? Is this a coincidence? It is absolutely not. Okay. I am going to tell you something that will sound crazy when you hear it the first time, but you will agree with me soon that it is not. I am going to tell you that these two facts, right, are actually one and the same thing. Okay. The fact that you created three particles without mass and the fact that three other massless particles, completely different particles, right, the G1, G2, G3 have nothing to do with, seems like they have nothing to do with the Z and the W bosons. The fact that these three massless gauge bosons acquired a mass, right, they turn out to be exactly the same thing. Okay. Because do you remember when we talked about what are the real propagating degrees of freedom of a massive gauge boson or of a massive vector boson? Remember, we had two transverse polarizations, right, but then crucially we also had a longitudinal polarization, right. And remember, I said that the longitudinal polarization is indistinguishable or is exactly equivalent to having a mass, correct. So, when you think of mass for a gauge, for a vector boson, right, you have to immediately start thinking about longitudinal polarization, because that mass absolutely shows up as the longitudinal polarization propagating degree of freedom. Okay. So, what has happened is that this is the phrasing, it might sound funny, but it is completely true. Okay. The Goldstones, right, in the theory, which are not there anywhere, that is another important thing. Where are the massless degrees of freedom, right? We made them, but then we do not see them anywhere in the universe, we do not produce them in the lab, right. So, that is because the Goldstones actually got eaten, people say this word in this context, okay, got eaten by the gauge bosons as longitudinal degrees of freedom. Okay. So, that is what has happened to the Goldstones. They did not go anywhere, they got reincarnated as the masses of the gauge bosons as longitudinal degrees of freedom. So, that is the degree of, the Goldstone is a degree of freedom, the longitudinal thing is another degree of freedom. So, absolutely that is what has happened. Okay. Now, this eating of the Goldstone bosons as longitudinal degrees is what is known as the Higgs mechanism. Okay. The symmetry breaking itself is not the Higgs mechanism. Okay. The fact that you have goldstones itself is not the Higgs mechanism. The fact that the goldstones that were hidden in the Higgs field got a new life as masses of masses of the gauge bosons, that is what is known as the Higgs mechanism. It is also known as, there were actually 6 people involved in 3 different combinations, more or less at the same time. Okay, they all proposed this at more or less the same time, and Kibble mechanism. All 6 of them got the J.J. Sakurai prize, which is a very prestigious prize in particle physics. They got it very recently, okay, about 10 years ago, if I remember correctly. But yes, they were all involved. So these 2 operated as a team. Higgs operated alone, and Guralnik, Hagen and Kibble operated separately. And since this course is being seen in India, let me also add an interesting tidbit, which is Kibble was actually born in Chennai, okay, in the British Raj times, but yeah, but he is British. Okay, fantastic. Now you might wonder now why Higgs alone actually got the Nobel Prize, Higgs and Francois Englert, right? Why didn't the others get a Nobel Prize? So we will see actually, okay, why it is justified that Higgs alone got the Nobel Prize, okay, among these. I mean, not just Higgs, but why didn't the others get a Nobel Prize? Okay, we will see so. Okay. Now we broke the electroweak symmetry and got a photon, a massless photon, right? And then I said we broke it down to electromagnetism, but then we began with things like hypercharge, right? So what happened to hypercharge? How did we suddenly acquire this new charge? We got this because it's actually charge itself comes from a combination of hypercharge and the weak isospin. Okay. So you can go convince yourself that the charges that we are assigning, okay, to the Higgs and to the I mean the electric charges we assign, right, to the Higgs, to the different quarks, to the gauge bosons in this case, right, all of them actually follow from this relation. Okay, when you actually break the symmetry, you can literally see this relation pop out. If you keep following where the hypercharge is and the T3 is, okay, I didn't tell you what T3 is, that is basically the third component of the weak isospin, right. So when you have these SU2 doublets, right, we write fields like this, right. So the Higgs field, for instance, we wrote something up here and something down here, right. So that's what we mean by weak isospin. This contains T3 of, I could even have called it I3 basically, okay, T3 of half, this corresponds to T3 of minus half. So every time we write a doublet this way, even the QL doublet, the UL had T3 of half and the DL had a T3 of minus half, okay. So that's what that is, and this is the relation between the hypercharge, the electric charge and the third component of isospin. Okay, so electric charge basically arises as a combination. You can just rewrite this, right? Arises as a combination of hypercharge and T3 as expected. Okay. Yet another thing that happens is that once I break the electroweak symmetry I still have to write down QED, right? What is QED? It is the interaction between matter fields and the photon, correct? So, where does that come from? That also comes from here. Okay. Sorry, it's not just from there, it comes from, you got the photon out of all this, but you still need to put in the kinetic term for the spinors, right? Use the covariant derivative and write down the kinetic term for the spinors, and you will end up with, I am going to write NC to indicate neutral current. Okay. All I mean is I am going to write down interactions between neutral gauge bosons and fermions, not the W plus and W minus. Okay, that would be a charged current. So that would give me, I am going to write a shorthand notation. This says that E is the coupling, okay, and A mu is the gauge field, and J mu is the what is known as the current, which involves fermion fields. Okay. So let me write down the shorthand expression and then I will give you the expansion of each of these terms. Okay. The Z boson, it will turn out interacts with two kinds of currents. Now again go back here and see what the coupling of the photon should be. Okay. So over here we had a combination, right, G1 squared plus G2 squared for the mass. Similarly, you can go work out what the coupling will be in terms of G1 and G2, and you will find that it is G2 sin theta W, which is the same as G1 cos theta W. In any case, this is all a fancy way of writing G1 G2 over G1 squared plus G2 squared under the square root. Okay. So that is what we see as electromagnetic coupling. Okay. And what is J mu of EM? That is nothing but summing over all fermions, the charge, that is the current. Okay. Agreed? This is what QED Lagrangian is, right? Now I am just summing over all the fermions that are charged. Now what is J3? That turns out to be gamma mu 1 minus gamma 5 over 2 F. So what is this fancy 1 minus gamma 5? Remember gamma 5 in our basis was this, right? It's a 4 by 4 matrix, remember? So if I have 1 minus gamma 5, right, all it means is I have picked out the left handed components. Okay, so if that is the right handed component, then that is the left handed component. I am only picking out the left handed components, which is what I expect, right. This literally stands for the current that the W bosons before symmetry breaking participate, and that those W bosons interact only with left handed fields, right. So that is exactly what this is picking out. Okay. And since the Z comes as a combination of both W and B, you end up with a combination that looks like this. So that the Z seems to act like the photon in some certain cases, but with a different coupling also acts like the W boson. Okay, good. So in the last 5 minutes, we are going to see yet another degree of freedom that we did not really talk about at all up to this point, which is the small h. Okay. So, where did the small h arise? When we wrote down the Higgs field in terms of components parameterized this way, right? Remember, around the vacuum expectation value, I expanded the I expanded the field, right? I took this as a fluctuation around the vacuum expectation value, correct? So, to give a further picture, that h is, so this is the vacuum expectation value, right? So, that h is basically the fluctuation around that. That is the degree of freedom we are thinking about. Okay. So, what is that little h called? This is the field that is known as the Higgs boson. Okay. Never forget this. When we started with a capital H, right, this is not the Higgs boson. This is just the Higgs field, okay, which is a doublet under the weak SU2, right? Whereas this is a neutral particle, right? Right. So, I do not even have to put that in now, correct? And this does not transform into SU2 or anything. This is something that you get after symmetry breaking, correct? So, this is electrically neutral, that is all you can say about it, right? But nevertheless, it is a quantum field and you will have a quantum excitation associated with it, a particle associated with it, and that particle is the Higgs boson, okay? And it is this Higgs boson that was discovered in 2012, okay, while I was doing my PhD. So, I wrote a paper around that time with a couple of other co-authors, with 3 other co-authors, and that happened to be my first paper that came out on the day of the Higgs boson. It was on the Higgs boson. So, most of us in the community knew that the Higgs boson discovery was going to be announced. We knew it about 6 months beforehand. Okay, so, most people in the community, the theorists at least, try to predict some interesting properties of the Higgs boson, and there were many papers out on the day that the announcement came, which was 4th July on that year. Okay. Let us look a little bit more into the potential that involves the Higgs boson, not the Higgs field now. So, I might as well write down the potential with an argument that is this, okay. So, that I can simply write as this, okay. How can I do that? Because remember, in the unbroken symmetry potential, I had mu squared h dagger h squared, right? And also we had V equals mu squared over lambda, correct? Lambda or 2 lambda? It was 2 lambda, right? So, all I have done is rewrite mu square now in terms of V, okay, and then singled out just the h terms. So, when you do that, you can simplify the whole thing to just this, okay. So, that now you have, clearly there is a quartic term, there is an h squared multiplying at h squared, but there is also a cubic term, h squared multiplying square root of 2vh, right, and there is a mass term, right. So, what is that mass? that is just 4 lambda v square with this normalization, right. So, let me end here by saying that this is the reason why it took people so many decades to discover the Higgs boson. Why? Because lambda is an unknown quantity. Okay, this is something you wrote down in the potential. We knew V. Okay, we know that V is around 246 GeV. This we know because this is basically, this comes from this is literally the Fermi constant, the square root of the Fermi constant inverse. And the Fermi constant was known from the days of Fermi, right, because he looked at beta decay and then characterized the strength of the beta decay with Gf, and ultimately we have resolved it into the Elter-Weak scale. So, this was known, but this was not known. This is an input that you put into the potential. So, because this lambda was unknown, the Higgs mass was also unknown, okay. And that is why even though the Z boson and the W boson, right, the W bosons, they were discovered when? They were discovered in 1983, okay. And notice that their masses go as what? They go as G, some G times V, right, and the weak couplings are known, the V is known, so their masses were known and you could build a collider and go discover them. But since lambda was not known, this was one of the main reasons why it took them 4 decades, rather 3 decades after the Z boson's discovery to actually discover the Higgs boson also. Okay. On top of this, the Higgs boson's collider signatures are non-trivial and so on, but this is the main reason why. Okay. So, I will stop here. In the next class, we will see how this Higgs boson interacts with fermions. All right. Thank you. See you in the next class.